In this video, we're going to wrap up Chapter 5 with Section 5.8, the inverse trig functions integration. In this section, we're going to integrate functions whose antiderivatives involve these inverse trigonometric functions. We're going to go back to Algebra 2 and remember that completing the square and use that to integrate a function, and just review the basic integration rules involving our elementary functions. Now, if we remember back to derivatives, we had the derivative of sine inverse, or arc sine. And when we took the derivative of arc sine of x, that derivative was 1 divided by the square root of the quantity 1 minus x squared. And the derivative of the arc cos function was the same thing, but it was negative. When listing the antiderivative that corresponds to each of the inverse trig functions, you need to use only one member from each pair. It's convenient to use arc sine of x as the antiderivative of this, rather than the negative arc cos of x. The next theorem gives one antiderivative formula for each of the three pairs. These proofs are left to the exercises. So here's the antiderivative that gives us arc sine. We have our du in the numerator, and our denominator is the square root of a squared minus u squared, and that antiderivative is the arc sine of u divided by a plus our constant. The antiderivative here for arctan is numerator is du, denominator is a squared plus u squared. When we figure out what a and u are, we plug them into these places. 1 over a becomes our fraction, and then the arctan of another fraction, u divided by a, and plus our constant. And then the final one here is for arcsecant. So a lot of this is when you are given an antiderivative, you have to look at what you are given and try to fit it into one of these formats before we can perform the antidifferentiation. Now I've copied the formula box up here again so we can see it as we're working on these parts A, B, C here in example 1. When I look at the first one in part A, I'm trying to see where it's going to fit, what pattern it looks like. And I see my numerator is dx, my denominator has a radical with something minus something. So if I come up here to the box, I can eliminate number 2 because there's no square root in the denominator. And when I look at my denominator here in part A, it's a simple radical with nothing out front, so that eliminates formula 3 here for arcsecant because of this u out front. So I know I'm going to deal with the first formula, which is going to be for arcsine. And I sort of want to make it fit this format. So I'm just going to rewrite my integral here a little bit. We have antiderivative. Our dx is up top. Underneath that radical, I want things that are squared. And I have a 4. And I can rewrite that as 2 squared minus x. And let me put what we're squaring in parentheses to sort of make it stand out. So I have something squared minus something squared. By my formula, this is my a value, and this x is my u value. So if u equals x, then du equals dx. So it looks like this one is all ready to go in the format we need it to perform this antiderivative. So I know this is going to be my arc sine of u divided by a. So this indefinite integral is going to be arc sine of u divided by a, or x divided by 2, plus c. Alright, let's look at letter B. In letter B, the first thing I notice is there is not a radical anywhere in the problem. And if we look back up to our theorem 517 box here, everything has a radical in it except arctan. So for arctan, we have our du over a squared plus u squared. We got to make this fit that format. So see, the first thing I have down here in the bottom is 2. 2 is not a perfect square, but we can always rewrite it as the square root of 2 quantity squared. Square root of 2 squared is 2 plus. Now be careful here. What do we square as a quantity to get 9x squared? Well, the square root of 9 is 3, and the square root of x squared is x, so that is the quantity 3x squared. So I'm going to come off to the side here and think about this as a u substitution. If my u is equal to 3x, then du would be equal to 3 dx. I have dx, but I'm missing the 3. So if I make this into a 3 dx, I'd have to balance it with a 1/3 out front of the integral sign. And now it looks like we are in the proper format to do the antiderivative. See, my du is my numerator, du is 3 dx, and I have in my denominator a squared plus u squared. A is equal to the square root of 2, u is equal to 3x. So I'm just ready to plug those u's and a's into my arctan formula. So I still have my 1/3 out front. And now I plug into my arctan formula, 1 over a, 1 over the square root of 2. And it's the arctan function. And then my fraction is u over a, or 3x, over the square root of 2. And then we add our arbitrary constant plus c. Now let's clean up a little bit here. We can multiply these leading fractions. That's going to be 1 over 3 root 2. We could rationalize that if we want to and have root 2 over 6. But let's leave it like this. And we have arctan of our quantity 3x over root 2 plus c. So we had to identify, the format and what inverse trig function we would use, and then play around with that to get it to fit the mold, so to speak. Okay, and the last one here, c. I see a radical in my denominator, and it's not just a radical. We have something else out front here. The arcsine formula has just a radical. So it looks like here we're going to be using arcsecant, because in the denominator there's a radical and something in front of it. So let's start looking at this one and breaking it apart. Under my radical I want something squared minus something squared. So here my 4x squared is going to be quantity 2x. If I square the quantity 2x, 2x times 2x is 4x squared. And then the 9 is going to be 3 squared. So going by this format, it looks like my u is 2x and my a is 3. So if u equals 2x, then du equals 2 dx. So it looks like I'm missing a few things here. For du, I need 2 dx. I only have a dx there, so I'm going to need a 2, and I'll have to balance that, of course, with a half out front. Or, I also need my u value to be a 2x. Here in the bottom, where I'm supposed to have a u out front of the radical, I just have an x. So I also need that to be a 2x. So instead of balancing out front of the integral sign with a 1/2 to make that multiply to a 1, it looks like I'm going to have to squeeze a 2 in front of this x. And then I won't need anything out in front of the integral sign to balance, because here I've worked completely to the right of the integral sign. 2 divided by 2 is 1. I multiplied the numerator by 2 and the denominator by 2. So in effect, I've done nothing to mess up my integral. So here, let me rewrite it. I'm going to have my antiderivative of 2 dx up top. That is my du. And then I'm going to have a 2x. And then under my radical, I'm going to have 2x quantity squared minus 3 squared. So again, here is my u, and here is my a value. And it looks like we're ready to go. My du is up top. This is u out front of the radical. So yes, it looks like we are ready. My arcsecant formula begins with 1 over a, or 1/3. And then it's arcsecant. And now after arcsecant comes a fraction, absolute value of u up top. So that's going to be the absolute value of 2x divided by a. A is 3 plus c. So I took what I was given, I identified which of the trig function formulas I needed to use, and then I played with what I had until it fit the mold. See here now in example 2 looks a little different. We have an exponential, an e to the x. And when I try to think about which of the formulas this is going to fit, it doesn't look like it's a good fit right off the bat. But let's see if we can play with it a bit. E to the 2x, how can I write that as something squared? Well, remember when you multiply like bases, you add exponents. So if I write this as e to the x quantity squared, or e to the x times e to the x, I'm multiplying like bases, so I would add the exponents. 1x plus 1x is 2x. So another way to write this e to the 2x is e to the x quantity squared, and then minus 1, and of course 1 can be written as 1 quantity squared. So as a u sub, this we're hoping is going to fit as our u, and this will fit as our a value. So let's see, u is e to the x. What is the derivative of that? Du would be e to the x dx. And let's solve this for dx. So divide both sides by e to the x. Dx would equal du over e to the x, which is the same thing as du over u. Du divided by u. And we say that's equivalent to dx, so we're going to plug that du over u in up here. So let's do that and see if it starts to fit any of our formulas a little bit better. We're going to have the antiderivative. This dx up top we're going to replace with du over u. And then in the bottom, underneath our radical, we have our e to the x quantity squared minus 1 squared. Now it might look a little different, but we're getting close to one of our formulas, and it's looking like it's going to be the arcsecant formula. But what we are missing from the arcsecant formula is this u out in front of the radical. But actually we do have it, but it is a little hidden, so to speak. This numerator, du over u. If I had a fraction as 2 divided by x, no, that might not be the way to go. Imagine it this way. There's a 1 up here as a placeholder. If I dragged this du over u out in front of the fraction, I would have du over u times 1 over my radical. And then I could just multiply straight across. So my du would wind up in the numerator, and this u would wind up in the denominator in front of this radical. So if we rewrite it using that method, we're going to have the antiderivative. Now my du is up top all alone. This u winds up down in front of the radical, u, and then we have our square root of e to the x quantity squared minus 1. Now it's looking like we are going to fit the arcsecant formula. And I should write out that our u is e to the x, and our a is equal to 1. So it looks like we're ready. Looks like we match the formula. Du up top. This is u, and then times the quantity under the radical, u squared minus 1. So we're ready to go. This antiderivative is going to be arcsecant. In front of arcsecant was 1 over a, and our a value is 1. So that's 1 over 1, and we don't even have to write it. Arcsecant, and then we have the formula says the absolute value of u, and our u value is e to the x over a, and a is 1. And we add our plus c. Now divided by 1, we don't have to write that. And now that we have it down to e to the x, do we need the absolute value bars? No, e to the x is always positive. So the absolute value bars are not necessary. Arcsecant of e to the x plus c. In example 3, if we look at this, it fits none of the formats at all. You know, our numerator is x plus 2. Our denominator looks good under a radical of 4 minus x squared, but that numerator is messing everything up. Now we have a single term denominator and a two-term numerator, so let's bust this up into two separate fractions. First, we'll have the antiderivative of our first numerator piece x over this denominator, and I'm going to rewrite that as 2 squared minus x squared dx. And then we're going to add to that the next antiderivative of this piece of the numerator 2 over that same denominator. And I'll rewrite that not as 4, but as 2 squared minus x squared dx. So now we have it broke apart into two pieces, and it looks like here on the right we might have one of our inverse trig functions going on. Over here on the left it might just look like a u sub from the fundamental theorem of calculus or section 5.5. So let's work on this left piece first. It looks like it might be a little easier. If we think about let's rewrite it as x times this quantity, and I'm going to rewrite it as 4 minus x squared to the negative half power dx. Well, in the parentheses is our u value. So the derivative of that would be negative 2x dx. So we have the x dx. We're missing the negative 2. I'll squeeze it in and balance it out front with a negative 1/2. So now we'd be ready to do the integration on just this part. So we'd have 1/2, and it would be u to the positive 1/2. When we add 1 to this exponent, from negative 1/2 would go up to 1/2. So we're going to have this quantity, 4 minus x squared to the 1/2 power. And then we would divide by the new power. Divide by 1/2 is going to be the same thing as multiplying by 2, or 2 over 1. These fractions will cancel out. And on the left here, there still is a negative sign squeezed in there. We're going to have negative and then this quantity. And I'm going to rewrite it under a radical. 4 minus x squared. So this piece here on the left we've taken care of. And that antiderivative, negative square root of 4 minus x squared. Now back to this second term. And this looks like it's going to fit one of our inverse trig function formats. To make it look more like it's going to fit the mold, constant multiple rule says I can drag this 2 out front, and I could move this dx up in its place. So we're going to have 2 antiderivative, dx is our numerator, denominator is a radical, 2 squared minus x squared is under it. So this looks like it's going to fit the arcsine formula. So we're going to have plus 2 arcsine, and then the arcsine is x over 2 plus c. And that would just fall down here with this other term, 2 arcsine x. I did forget my c in there. Of a half x plus c. Here in example 4, we're going to have to remember back to, well, we did this earlier in pre-calc, and you might have seen it in Algebra 2, the method of completing the square. Complete the square helps when quadratic functions are involved in the integrand. For example, the quadratic x squared plus bx plus c can be written as the difference of two squares by adding and subtracting half b quantity squared. And we come up with our complete the square. This you might not remember too well. Let's do the completing the square here on this denominator, and hopefully it'll come back to you. What we want to do is force that denominator to be some quantity squared plus some other quantity squared. We want to break it up into the sum of two squares to make it fit our formulas. So I'm going to come over here and do a little scratch work. Let me get this up out of the way. And we're going to do completing the square on that denominator, because right now it's a nasty polynomial, but we want to make it look a little more useful for what we're doing here. So here's our denominator, x squared minus 4x plus 7. Now what I sort of want to do is move that 7 out of the way and leave a little opening. So I'm going to have, minus 4x. I'm going to leave a gap here, and my plus 7 just sort of got slid over. Now to find the term here that's going to make this perfect, we take our middle term, this middle number, and we want to chop it in half and square it. So it's negative 4. We're going to chop that in half to negative 2 and square it, and that squared becomes a positive 4. And if I add 4 here, so I don't mess up the integrity of this polynomial, I'm going to subtract 4 over here. So I added 4 and subtracted 4. I basically changed nothing. But what I did do here is this part. I turned that into a quantity squared. And that quantity is x minus 2. Quantity x minus 2 squared. And then we have our 7 minus 4 is plus 3. Plus 3. Or you can think about that as the square root of 3 squared. So this polynomial in the denominator I can now rewrite as, our numerator is dx. Down in that denominator we have a quantity, x minus 2 squared, plus the square root of 3 squared. Does it look a little more like one of our inverse trig function integration formulas? Yes, it does. Denominator has no radical in it. That's a dead giveaway. This is going to be arctan. So, what is our u and a values? Well, here's u, and this would be a. So u equals x minus 2. The derivative of that would be 1 dx. So du and dx are interchangeable. So let's do this as a full-on u substitution. This dx is now du. And then we have in our denominator u squared plus a squared. Does that look like our formula? A little cluttered here. Yeah, here's our arctan formula. Du over something squared plus something squared. And that's exactly what we have. So we're ready to find the antiderivative, and that is 1 over a, or 1 over the square root of 3, arctan, of u divided by a, and our u value is x minus 2, divided by a is the square root of 3. And don't forget to add your arbitrary constant.